Hi everyone. Today we're going to talk about resistors, and we're not going to talk about the same old boring crap that you hear every single day, all that regurgitated information that you can find anywhere on the internet, i.e. resistor color codes and working out wattages and looking at resistor calculators. That's all real standard stuff and very easy to find. Today we're going to talk about the stuff that they really don't teach anywhere, and why they don't, I have no idea, because this stuff is equally important as working out wattages and knowing the actual resistance of a resistor. Putting the wrong resistor in circuit can make or break your design. If you're repairing something, it can cause it to work erratically. If you put a wrong resistor in an oscillator, it'll completely stop it from working, and it'll, cause you to scratch your head for a long period of time trying to see why the oscillator isn't working. Because resistors are not only resistors, they are inductors and capacitors as well. So today we're going to take a look at a whole bunch of different types of resistors. I'm going to show you how to recognize them, tell you what circuits different types of resistors should be in, and what kind of circuits certain types of resistors should not be in. This is very, very crucial to know whether you're just a repairman, whether you're a designer, whether you're working with surface mount stuff, whether you're working with through-hole stuff, whether you're working in even majorly large power supplies. Everything. This is very, very important information to know. Now, you know yourself that you can find information about resistor color codes and wattages all over the internet. I've done standard videos about working out resistor color codes and making it simple. That's on my regular YouTube channel. But I have never really gotten into this aspect of resistors, and this is very, very important to know. And I find these mistakes all the time. It's amazing how much I find the wrong resistors in circuits, and it'll do things, as I say, like stop oscillators. It'll make RF sections desensitized, and you wouldn't even know it. You put the resistor in and it works, but it's down 6 dB. It's working, but it's down 6 dB. So, it's there. The signal is there. So unless you really were to get into it and start measuring gain and things like that, you wouldn't know. So there's a whole bunch of different aspects about resistors that are very, very important to know. So what I'm going to do is I'm going to gather up a whole bunch of different styles of resistors. I'm going to show you how to recognize all the different ones, and we'll talk a little bit about each different one, even these big, huge ones like this. So this came out of a broadcast transmitter. I've got a box full of these things. So let's get started. The first resistor, inductor, capacitor that we're going to take a look at here is, care to take a guess what type of resistor this is? This is a metal film resistor. Very, very quiet, great in high gain stages. So if you're going to design a microphone preamplifier, or if you're working on like a phono stage, something like that, great resistor to use. They are very, very quiet. Not only that, they're very temperature stable, so they're great in oscillator circuits. Now, of course, because this is a resistor, inductor, capacitor, they're only good up to certain frequencies, and I'll talk about that here in just a little bit, and also tell you why this is a resistor, inductor, and capacitor all at the same time. Now, the coloring system on these, because this is such an accurate rating, it's a pretty standard. A lot of the offshore resistors that are coming over here now have lots of resistor color bands on them, and it's kind of silly. This is still a really standard way of reading things. This is the way they should all be, but take a look at this here. So I'll use this as my pointer. So we have gray. All right, gray is 8. Red is 2, green is 5, so 8, 2, 5, and then we have brown, which is the number 1, and then we have a space here and another brown, which is number 1. So we have 8, 2, 5, and then we turn this number into the number of zeros. So since this is the number 1, brown, we turn that into 1, 0. If this was red, we would turn it into 2 zeros. All right, so we have 8, 2, 5, 0. So it's 8.25 k ohms, and then there's this space here which tells us that this is the accuracy band. So this is 1% tolerance. Very, very nice resistor. These are great resistors to use in all sorts of different types of circuitry. Now, the reason that I talk about this thing being a resistor, inductor, capacitor is because underneath here we have two caps. So there's a cap on each end, and the space between the two caps forms a capacitor. Now, if we cut some of this surface off, we'll see under here that this is a helical construction under here. So if we look at from this end to this end here, we're going to see what looks like a wind, almost like a coil, and that forms an inductor. the lead length on a resistor at certain frequencies can be an inductor. This is an antenna at certain frequencies. You know, if we're going to be going up into the gigahertz, you know, that would be an antenna right there, right? So it's very important to know what the maximum operating frequency of the resistor is, you know, and of course, if you're going to be using this in an oscillator or something where lead length is going to be prohibitive, like, you know, this would be an inductor, right? You want to shorten up the lead length and things like that. And in future videos, we're going to talk all about this stuff as we start to make some extremely high frequency oscillators. In understanding high frequencies, once you understand how RF works in circuitry, understanding audio circuitry is all that much easier. It's because you've kind of gone to the next level beyond that. So it's kind of like you're looking down on the audio stuff because you understand how these operate at a higher level, at higher frequencies. I'll get into explaining that a little bit more as well. A lot of people think that they can just cap off their knowledge in the audio range. If you bring it to the higher frequencies, to that step above, a couple rungs up the ladder, then you can really go, oh, I can see how that would affect an audio circuit. So what I'll do here is I'll take these very sharp EREM clippers and I will try to trim some of this off so that we can see some of this helical stuff under here. Hate wrecking good resistors, but I got a whole bunch of these. Oh, there's a cap on the end. I got a little bit of it off there. I don't want to wreck the helical design under here. I want to keep that all together. Oh, it's coming off. It's hard to keep this all in focus because this is so zoomed in. So this is 135 millimeters right now, so this is like some pretty crazy zoom going on here. As you can see, this size of my hands, I look like a giant in this thing. So here we go. Come on. I hope this is going to have enough magnification to even see this. Boy, this is, you can kind of see a helical wind in there a little bit. Sorry for the shaking. Let's try to get this all off of here. Especially when it's zoomed in, any kind of movement just looks crazy. Boy, this does not want to come. They really coated this thing well. Such a shame to destroy this thing. There it is. You can see the helical wind right in there. See that? That's how they trim these. That's how they adjust them. All right, here we go. There you go. You can see the helical wind there. I'll just get my other resistor as a pointer. So you can see the helical wind under there. See that? How it's wound? Right there. Fuzz on my hands here. See that helical wind there? So it's winding around the resistor. So this is very common, even in this particular style of resistor, you're going to find that type of helical wind. We'll talk about this type of resistor here in just a moment. So that helical wind forms an inductor. That's adding length, right? Anytime you're having any type of a coil, you're forming an inductor. So that really makes these things rough to use at higher frequencies. And this is why carbon composition resistors are used at some very, very high frequencies, because basically it's just a carbon plug in the center and then two leads that go into each end, and they work very, very well for you know, dummy loads and things like that. Whenever you're working with a large dummy load, they're not helical wound like this at all. Here, I'll grab one of these things. Think a big dummy load like this thing right here, right? So when you're dealing with this, there's a big carbon resistor that fits into this thing here, and then usually there's a set screw. Is there a set screw to tighten it in? Sometimes it's right up at the front. I don't know where the set screw is in this one. Maybe it's just pressed into this design here. Oh, there it is. There's a little set screw here that tightens it down. A little set screw there, and it presses this so that you get a good connection there. And yeah, so at any rate, here it is, the one at the other end here. Right there, that's the other one there. So you had to tighten the thing in here so that it, you know, it works very well. So again, you know, big carbon resistor inside this thing, and, you know, spaced close to this thing so that this thing can radiate the heat. I can back the zoom out here a little bit so we can take more of a look at this. So we can get rid of heat, right? And as you can see, it's a termination for microwaves, you know, microwave frequencies, you know, when it's 100 watt. I have a lower frequency connector. This is classified, well, they're good into the VHF range. Sometimes even if you push them, they can go pretty high, but, you know, this is good into the VHF range kind of area here. The connector that's on here is known as an N connector. that is what you use for microwave stuff right there. It has a little pin in the bottom and it's got this extra shield. Very important to keep the impedance the same all the way through. If you change the impedance, just the impedance difference in this barrel here, if you look at this with a time domain reflectometer, you will see any impedance bump in here. And if there's an impedance bump in here, you know, of course, that's an issue when you're dealing with microwave frequencies. So very, very important to keep the impedances uniform, all the way the same. So you don't want any types of impedance bumps, and connectors are bad for that. Some cheap connectors, you can get BNC connectors that are used for video application that their impedance is all over the place. So since we're talking about resistance, I may as well talk about impedance because it's AC resistance, right? So here, let's grab one of those connectors that are all over the place. Okay, so when you're making cables that don't rely on frequency, you can use some of these things. And so this is a BNC connector that, you know, it's great connection, little gold pin in the center, right? You know, they unwind and you see this here, impedance in outer space. This open area here, you know, it's just like, you know, the difference between here and the barrel. And of course, you know, you crimp the shielding here. See if I can get this a little bit closer. You crimp the shielding in this thing, and then, you know, you've got that open piece of coax to here. You know, it's a huge impedance bump here. And then, of course, you know, it's, you know, as you start to go higher and higher in frequencies, things like that start to matter. BNCs that are, you know, correctly designed, when you put the thing together, you actually fold the coax around the shell, and the center pin is already soldered on, and you press the whole thing together and usually thread in an end, and those things are very good, you know, right into the gigahertz region. But then, you know, this thing here, you know, these are designed for video surveillance cameras, right? So what I did with one of these is I think I used one of these things and I made it into a TDR, time domain reflectometer. So I did lots of measurement and moved things around, and anyways, I'll get into that here in a little bit. So, and you know, we may even design a time domain reflectometer. I'll see how interested you guys are in that. I did a video on one, but I haven't released all that much information on it. Everything is in the head. All the circuitry is a little high voltage supply, and a little transistor in here doing its little avalanche thing. And anyways, we'll talk about impedance here in a little bit as well. I might even use that as a demonstration here to show you how much, you know, just a little bit of impedance difference makes. So very, very important. Again, you know, impedance is AC resistance, right? Just like I talked about earlier. I've put together two 50 ohm terminations, or dummy loads as they're known in the RF world, for us to test or analyze on this 50 ohm analyzer right here. So we're going to test both of these resistors at RF frequencies, and I want you to figure out which one of these is not going to work correctly at RF frequencies. So I'll tell you a little bit about each resistor, but I want you to take a guess at which one you think is going to work correctly. So 50 ohm analyzer. Now this is a relatively low frequency, so lead length is not going to mean too incredibly much down here. So that's a little bit of a hint there. So first of all, we have a 50 ohm resistor right here. This is rated at 20 watts, and it's just fastened into this connector right here. So there's a closer look at that resistor. And there's a 1/4 watt resistor. I'll turn on this light so you can see down in there. There's a little 1/4 watt resistor down in there. It's actually a 47 ohm resistor, but I graded a whole bunch of different resistors to get one as close to 50 ohms as possible. And this one is 49 ohms, 49 point something ohms, and so is this one here. So they're both really, really close. In fact, I have the meter right here so I can show you this. I can get a good connection on the barrel here. So, you know, 49.4, right, we'll say. And this one here is 49.86. So close enough to 50 ohms for what we're doing. No problems. I'll just get this out of the way. Doesn't need to be on the bench. In the way. So which one of these do you think is going to work correctly? Let's try this one here first. So I'll put this on like so. Okay, so 50 ohm resistor showing 50 ohms. Reactance is 183, whoa. And the SWR is 16.0 to 1. If you were to hook this resistor up as a dummy load onto a small transmitter, you would destroy the finals in that transmitter, even though it's 50 ohms. So this resistor is a resistor, a 470 picofarad capacitor, 471 to be exact, and a 15.8 microhenry inductor, all at the same time. So it's a resistor, capacitor, inductor. This is a real common mistake that a lot of people make in the RF world. This causes a lot of damage. This is very common. I'll talk more about that, this particular type of resistor and other types of resistors that people make mistakes with all the time. So let's try this little quarter watt one in here. Put this on here. I should have changed the display first. Let's get that back to the normal display and we'll go in the same direction. There. Look at that. 49 ohms, flashing 50 ohms, X equals 0. Perfect. 1.0 to 1 SWR. Reflected power nil. This thing is your friend in the RF world. Mind you, it's only a quarter watt. It can only deal with, maximum quarter watt, but still, for an RF dummy load, this is how it's supposed to look. We want something that's purely resistive. Okay, we don't want capacitance and inductance and things like that. We want something that's purely resistive. So let's take a look at the capacitance. Zip for capacitance. And zip for inductance. That's what we want. We want something that looks purely resistive. And that's what that resistor is doing. At least in the RF world. If we take a look at, turn this on again, if we take a look down at that resistor again, that is a carbon composition Allen Bradley style resistor. So that's what we want to see. So next I'll explain a little bit about both of these resistors and why we're seeing what we're seeing. One very common mistake that a lot of people make, and I can see why. It says 50 ohms right on it, and some of these large resistors say 75 ohms on it, and those are two very common impedance ratings for RF systems. So 50 ohm systems is most ham radio stuff, broadcast transmitters, CB radios, all that kind of stuff is on 50 ohms. And 75 ohms was used for cable systems and things like that, right? So two very common ratings. So it is pretty common for people to look at this and think, oh, I can use that as a termination or something like that. Well, that's pretty far from the truth. Reason being is because this thing here has got two bands on each end, and what's the problem with this? Just like I explained earlier when I chipped away the coating on that resistor, what's going on in here? This is a wire wound resistor. There's actually wire wound around this like this. So that same helical kind of thing going on. Now, when we looked at that other very small resistor, there's very few, if you were to look at it and count those as turns, you could look at this very few turns on there, and it's really small. So the difference between something like this and something like that is if that small resistor was rated at 50 ohms, you could still use that up to some very high frequencies. This thing here is so big and it has so many turns on it that this thing looks like a really bad inductor and capacitor and resistor at RF frequencies. This thing is ugly at RF, and even at low frequency RF like we saw, it's 1.8 something megahertz, right? So whenever you see resistors like this with bands on the end, rule of thumb is they're most likely going to be inductive, even if they say non-inductive. Why is that? Here's another trick that they don't tell you. Everything is an inductor at some frequency. So this may be non-inductive, looks non-inductive maybe in the audio world or very low RF frequencies. But just the size of this thing and the rings, it's definitely going to look like an inductor somewhere. So whenever you're wanting something that is non-inductive, you want to stick to some form of a carbon-style resistor. Now, again, everything looks like an inductor somewhere. If I find this resistor that I chipped apart here earlier, this little resistor right here, even this looks like an inductor at higher frequencies. It just all depends on what frequency you're at. So at low frequencies, this thing would look purely resistive, like that little resistor that I had in here, the little Allen Bradley resistor, right? So it's just all about frequency. Now, this thing here is so incredibly big. The reason I chose this really large resistor is because it really amplifies the problem and really gives us a good example of the differences between the two. So when you see resistors like this with rings on the end like this, or like this right here, or I had that really, really large, here's another one here. You can see this one, you can actually see the wires going into this one. These things are inductive, and you don't want to use these things in RF service at all, even if they are labeled as non-inductive. Here's another big trick. These things, manufacturers call these things non-inductive sometimes. This thing is a wire wound resistor, and it's in this aluminum sort of a shell. It's designed to be bolted to something where this thing can get rid of a lot of heat. You know, it's a 50-watt resistor. So this resistor, if it was 8 ohms, would be fine to use as an 8-ohm loaded audio, even though it's wire wound, because again, even though it's wire wound, it looks like an inductor at certain frequencies, but the frequencies are so low that it doesn't matter. To give you a comparison, if you're thinking, well, how does this work? Think of a speaker. What is a speaker? It's a bunch of coils of wire wrapped around a magnet, right? Really, really low resistance as well. Very low impedance as well. So these things cannot be used in RF service, just the way they're put together. You know, like maybe extremely low frequency RF service, something like that. I would have to sweep, if this was 50 ohms, this is 1K. If this was a 50 ohm resistor, you'd have to sweep it to see where things start to go nuts. It would go crazy at a really low frequency. And I see people buying these things that say 50 ohms and using these as RF dummy loads all the time. And when I see that, it's just a facepalm moment. It's like, what are you doing? And then they put the thing together and it's got a, you know, it's 1.8, 2 to 1 SWR. And they're well, it says it's non-inductive and it's 50 ohms. And that's the difference between being in the know and not being in the know. And I see it all the time. And I mean all the time. People buy these things and try and use these as dummy loads in the RF world. Absolute not. You can't do it. Don't do it. Inductive resistor. When you see these things, these are wire wound. Again, going to be fine at audio frequencies, right? For example, when you look in a power amplifier, you'll see these things in the output stage. You'll see 2 of them usually. Sometimes they're in a little ceramic package with 3 legs on them, right by the output transistors. Wire wound resistors, absolutely fine at audio frequencies. If this was a 50 ohm resistor, you could not use this 5.1. If this was a 50 ohm resistor, you could absolutely not use this in the RF world, because this is a whole bunch of turns of fine wire inside this thing. Oddly enough, it says CB on it. It has nothing to do with the CB. It's part of the manufacturer. This thing, 20 watts. Inductive like crazy. Can't use any of these things. These are all wire wound. Every single one of them. This thing's wire wound. It's all, everything you see. It's just wire wound like crazy. All of these things. Even that big one that I had, where did I put that one? That one was a monster. Moved it over here because I was knocking it around. This thing is wire wound too. Look at this. Huge resistor. So, what does that tell you? Definitely not good at RF frequencies. Maybe really something really low. So, now, here's something that's very interesting. In some of the large broadcast transmitter facilities, they use stove elements, but it's a tuned load. So basically what they've done is they've tuned it. So they take huge stove elements, the ones that you find that, you know, they kind of go like this, you know, and they fit in your stove, the electric stove elements. They kind of make that kind of a U. And they have a whole bunch of them. And they're all stacked together like this with a blower fan on it. And they're tuned, and it's a big tuned dummy load designed to, you know, deal with 25, 50K, whatever. You know, I've seen them just huge, big blower fans and exhaust openings on the sides of buildings. You know, those little grates that when fans start to blow, they kind of pop open, big, huge ones. So I'll just zoom out here. So big, huge ones, they're big, huge, and then they open when the blower fan starts up, and, when they click things to, to try and test things out so that they're not on the air, they feed these huge stove elements, and of course, you could heat the facility in no time at all by feeding, 50 kW into something like all those elements. It's a lot of heat right now. But again, those stove elements, they are inductive, very inductive, so they have to be tuned. So a different situation. Now, throughout time, as we're building RF circuits here at all sorts of different frequencies, you are going to get a feel for resistors that work in certain areas. And I want to share all that with you. I want to share all my thought process and everything with you guys so that basically you can look at this stuff and go, okay, this thing will work at a certain frequency, no problems. This would work at a certain frequency even though the resistance is off. Something like that. You could look at all these things and just recognize this. And over time, throughout our builds, you are going to get a grasp on all of this kind of stuff. In my world, I look at this and then I just go, okay, this would work here. This definitely wouldn't work anywhere. This is 1K ohm. And look at all these different types of resistors and know the ratings, and I just know where they would work in the frequencies, and that's just because I've done so much work with RF. Lots and lots of work with RF at many, many power levels. Some are extreme power levels. So, at any rate, these resistors are all inductive style resistors. We'll take a look at some non-inductive style resistors, and I will talk about them here in just a moment. Here are a bunch of resistors that are okay in low to medium frequency RF service and absolutely fine in audio service. I'll start with this one here and I'll explain a little bit about each resistor. I'll just go down the list here. So this is a roundie, and I've talked a lot about roundies in the past. This one is a brand new one, and this one has been kept out of the environment. So this one here is pretty close to its value. Brand new leads. They're a little bit bent up, things like this, because it's probably been twisted into a circuit or something at some particular time for an experiment. And it's been rolling around in a bin of resistors, ceramic resistors, so the body's a little bit beaten up on it. But these resistors here suffer from moisture ingression. So moisture can get through these things and it causes them to move all over in value. So if these have been in a controlled environment, like in a house or something like that, where it's been kept warm, and it hasn't been in a driveway or a carport, usually they're okay. What I do to verify these things is I'll get an old radio receiver and I'll test about 5 or 10 of them. And if they're all okay close to value, usually it's good to go. That tells you a lot. If you were to test a resistor like this and maybe another one, say this one here, this is 30K ohms. So 30 and then 3 zeros and then 10% tolerance here. So this is 30K ohms. So if this was, say, 40K ohms or something like that, I would question it. And then I would test another one and I would look for other resistors like that. So usually when these things move, they do move. So this one here is pretty close. I think this one's 31K ohms. It's very, very close to its value. So no problems with this one here yet. And when they're like that, they're usually silent and they stay like that. This one here is a metal oxide resistor. These are great resistors, and they're very stable. Not as stable as the metal film. Metal oxide is very good. These are becoming very common nowadays, and they're really good in RF service as well, but they can't go incredibly high in frequency, again, because of that helical thing and the actual size of the body itself. But, again, really, really good resistors. So, those are resistors to definitely have on hand. These are carbon composition resistors. These are Allen Bradley style one. They have a coating on them, so they're sealed up, and these stay pretty close to value. At least these ones do, and this one here too. So these are pretty high quality Allen Bradley style resistors, 5% tolerance, and they're very close to their value. So these are pretty good. Not as susceptible to environment, but they still are. Right? If it's been in a pretty harsh environment and been exposed to the weather, something like that, you can expect these things to be all over the place. But great resistors, 2 watt and 1 watt rated ones here. Another metal oxide resistor, very good quality resistor, kind of a porous shell on these things though. So if you were to say have a whole bunch of these things in a power supply and it came out of a CNC machine and there was lubricant or oil all over these things, they do move in value. Something to always keep in mind. And it will even get into these ones here. But these ones are very bad. So this is a very porous coating on it. I don't know if you can see that. It feels kind of like a powder on it. And yeah, they do soak up. If any kind of chemical or anything gets on here, these things will move in value, or they'll just completely open, just depending on where they are. But they're good resistors, again, as long as they're kept in a controlled environment. This is a great resistor. It's a little bit burnt, as you can see, because it came out of, where is the thing now? Right here. Came out of one of these things. So this is the actual resistor that fits inside this thing, and this will work right up into the microwave frequencies. So this is a carbon resistor as well. It was tightened down by that little nut there, and then the actual jack fits right onto the end here. There's a little cup that this fits into, and the whole thing is tuned. So this one here is has been heated at some time. I got a bunch of these things, and somebody had abused these things pretty bad. I don't know how much power they were putting through these things, but some of these resistors are almost right open. I think this one here is over 50 ohms. That's the reason it's out of here. Yeah, 52 ohms, right? So that's a ways off. So at any rate, these are a really decent resistor for RF service as well, right? As you see, like, these things go right up into the gigs. So, but again, these things are in an area that's tuned. So, it's 50 ohms all the way through, 50 ohms impedance all the way through. There is no, you wouldn't see, if you were to hook this up to a TDR or something like that, you wouldn't be able to see any impedance issues inside this thing unless you were to go extremely high, maybe 10, 15 gigs above its, its rated value there. So here is a carbon film resistor. These are very good. These have got a really tough shell on them, and they have to sit in a contaminant for a long period of time before they get affected. I find that these ones get affected before these ones do. So a lot of these accurate values are used in different type of circuitry. Like, again, this one here is a metal film resistor, and they're used in sense circuitry, things like that, where you need to have where these are, say, hooked up to a comparator, something like that, whereas if voltage moves a little too high, it'll trip an alarm, or if it's too low, it'll trip an alarm. So these are designed to keep things very, very accurate in circuit. And yeah, these things, they do soak up coolants and all sorts of contaminants. So these are, but these ones here, they're not as bad. I find that these things here will deal with, contaminants quite a bit more. Same with this type of a shell right here. Again, carbon film, helical thing. They have to get the helical design going on inside again. So, in RF service, a resistor this size as a carbon composition resistor would be a better choice in RF service. But again, when you're dealing with, lower frequencies, it's not too big of a deal. These things will work fine right up to 50 megahertz, something like that. Not a big issue, right? Sometimes even beyond as well. It's just depending on the design and the size of the body. The size of the body is a real determining factor. If you were to try and make something like this, say, work up at 400 megahertz, something like that, you have so much exposed area here in the helical design and the caps on the end, which form capacitors. And then, of course, you'd have to bend this around and attach it to a shell or something like that. You're going to start to see, issues with impedance. So size matters in RF big time. To give you an example, if you wanted to make something like this work at a very high frequency, what I've done is I've taken 1206 style resistors and I've soldered them from here to here. So it's just a 1206 style resistor right across here. And that works very, very well for the very high frequencies. So if you get a 49.9 ohm resistor or something like that, X equals 0 and the impedance is right at 50 ohms. Pretty much throughout the whole deal. Pretty good. Talk more about this. We'll design dummy loads and things like that for all you RF guys out there. I'll get really into this kind of stuff in the future. Again, RF is a really important thing to understand no matter what you do in electronics, whether you're an audio guy, whether you just want to deal with DC, whether you're just, dealing with power supplies. RF is very important to understand because switch mode power supplies are RF generators. Those things are hash machines. They create hash all over the spectrum. So understanding RF will help you eliminate that. Getting rid of common mode noise and stuff like that is a huge issue. And again, I'll get right into all that kind of stuff in the future here. So this, I could keep talking. I could make one continual video that would go for months just talking about all these different aspects, right? So it just goes and goes and goes, right? So, and again, this one here is another one of those metal film resistors, really good in all sorts of things. Great in for stability, temperature stability and things like that. If you want to build an RF oscillator that has, coils and all that kind of stuff, and you put it in an oven or something like that, keep everything temperature stable, these would be the resistors to go with. These things are absolutely wonderful to work with. And, a lot of them, they've got extra bands, and, they're really accurately rated, 75.3K, things like that, right? So not a problem if you need a 75k ohm resistor or something like that. The 0.3 really doesn't matter. The fact that you're using a metal film resistor in an oscillator or even an audio amplifier, like a high-end preamp or phono stage or something like that, is just good stuff. These are great. Out of all the resistors here, out of all of these resistors, these are the best for silence. Very, very silent resistors. And there's a lot of audio foolery going on about there. People order these special resistors that are square, and I'm not going to name any names of the resistors. They've got leads hanging off, and they're classified as low noise resistors, and you're going to get really close to the same performance out of this. And I'm talking really close. So, you don't go wasting your money and falling into that kind of a trap. I can see where it's very easy. So many people talk about this stuff, and they say, oh, these resistors, and people, they clamor onto that piece of information, and then they repeat it. And then you hear it so many times that people take it for true. And I find this in so many different areas of electronics, mechanics, everything like that. The best one here is, here's a little thing for you car guys, okay? So when you look in the paper and you see an engine and it says 4BBL, well, what do you think of 4BBL? Well, that's supposed to be 4-bolt block. That's what it originally started as. But somehow it got misconstrued into 4-barrel carburetor, 4BBL. How does BBL, 4-bubble carburetor? BBL was originally 4-bolt block. But again, throughout people and misconstruing throughout time, it just 2BBL became 2-barrel carburetor. 4BBL became 4-barrel carburetor. So there's just an example of how things get stretched and moved out through time. At any rate, so enough of that. So these resistors, great for audio service and pretty decent in RF service. Here's an example of how choosing the incorrect resistor can really affect circuitry. To do this demonstration, I'm using a time domain reflectometer that I've designed quite some time back. I use this to calibrate my oscilloscopes. I have calibrated pieces of coax. I'll explain more about that in the future. I did a video showing exactly what's inside this little head unit and the main power supply here. I've never released any circuit boards for this. I did this many years ago and they're in my old computer. If there is any interest in trying to build one of these things, I will get the files together and put something up. This is a high voltage power supply right here, and this is a very fast pulse generator right up here. So to give you an example here, I've got quite the run of coax in my hand here. And I've got a little joiner to extend it so that it's, the picks are further apart on the screen. So what's going to happen is this is going to create a very fast pulse at this side of the screen. What's going to happen is the signal is going to run down the coax, which is this line right here, and it's going to hit the end of the coax, and we're going to see a reflection. The reflection will be that little peak that we see at the end there. So what I'll do is I'll turn this on. So this is the original pulse created by this little device right here, and this is the signal running down to the end of the coax and reflecting. Now, by using the scale on the oscilloscope here, you can calculate exactly how long this piece of coax is. So all you need to do is just determine the velocity factor, and I explained that in that earlier video. So that's in my videos list on YouTube. It's done years ago. So at any rate, I won't get into that, but I'll show you the effects of impedance here. So this is open right here, and that's a reflection because this end is open. You can almost look at this like radar. It's like the signal's coming down here and it's hitting the end and it's reflecting back because there's nothing here to really soak up that energy. So if I take a 50 ohm termination, this is a 50 ohm system. If I take that 50 ohm termination and just put it onto the end here, look at that. The reflection is gone because this is terminated into the correct impedance. It's not like that signal's hitting a wall and reflecting back again, right? That open connection. So you can see here, if I short this here, I'll just put this in the end here. So you can see if I short this out here, I'll get inversion. So you can also see if a piece of coax is shorted out because the signal will go down on the bottom here. So just say you're going to look for a huge roll of coax, or somebody has a big roll of coax for sale, and you don't trust the fella. Maybe he's got 50 feet wrapped on the roll, but underneath there is a bunch of packing or something, and you don't trust the guy. I've run into situations like this, and I've brought this thing along just to make sure. So what you do is you cut 1 foot of the coax off and determine the velocity factor of that coax using this unit. And then you take that and you use that to determine the length of the roll. So it'll work it right out to, like, you say 727 feet. Like that. It'll work it right out just like that. And you can get much more accurate than that as well if you like. So a very handy device to have. So it's what would you call it? It's like radar for wires. So at any rate, so here's this resistor, this 50 ohm resistor. So we saw what it did on that analyzer, so I'll put it on here. And as you can see, it does nothing. It actually adds length. You see how that pick moved a little further away? It's adding that length because of the wire and the resistor. Right? So you can work out all sorts of things with this. You can see, impedance issues in the coax. So if I do this, you can see that we have a whole bunch of little bumps here all over the place. You can see this little bump right here. That little bump, the pronounced bump right there, is this connector. So if I remove this, you'll see the pick move closer. Let's take this off. Shorten up the coax. You see how it's right there now? So I'll just turn this down like so. And you'll see when I add this other piece of coax, you'll see it lengthen up. It'll push the pick further away. If I can get this BNC connector back on again, there we go. And there we go. So that's the added length of that other piece of coax. The reason I have 2 pieces of coax here is just so I can get those PIPs further apart so that it looks a little bit better on the scope for the demonstration. So now if I take one of these other terminations that I put together with the resistors, so I'll add one of those to this right now, so we'll see what happens with this. You can see that that's looking pretty good. All right. Now if we take the other one, which is the carbon film, that was the carbon composition. If we take the carbon film, you can see that we have a little bit more of a bump there due to this spiral going on. Added length. Put this one back and you can see that it's looking a little bit better. So again, extremely fast pulse. We're dealing with, this is 5 nanoseconds per division, so you can see how incredibly fast that pulse is. So you can see the effects of a really well-tuned system. Like this is a true 50 ohm termination right here, and it just makes it ever so smooth right at the end. No problems whatsoever. Whereas if we just take a normal 50 ohm wire wound, you saw what it did. It actually pushed this away. So very important to choose the right resistor, because if not, as you can see, big problems. Here's a quick peek at the pulse generator inside this little TDR head. That's it right there. You can see the little upside down SOT23 package transistor. It's upside down so that there will be clearance for the shell. You can see how each leg of the SOT23 package transistor is standing up on these little jade-colored inductors. You can actually see the helical wind of little jade inductors there as well. So lots of care and attention putting this thing together to get that pulse looking right. This is basically tuned, you could say, to make that pulse look the way it did. Make a nice clean pulse coming out of this. So I use this little device to, again, calibrate oscilloscopes, and to do measurements and things like that. So it's real handy. I have lots of calibrated lengths of coax, so when I calibrate the screen on the oscilloscope, I can use that to make sure, the time base is working correctly and everything like that, right? Handy little device to have around. This is the high voltage power supply here. Again, if you want to see inside all of this and you want more detail on this, just look in my video lists for TDR, time domain reflectometer. You'll find it. So quite a bit of information there. Whether you're repairing a piece of equipment or designing a new piece of equipment, choosing the correct VR or variable resistor or potentiometer for the job is very important, especially when you're trying to control some current. This is a really large wire-wound VR with a wiper on the back that has a carbon brush. This would definitely not be suited for RF purpose. This is another wire-wound VR. How do I know? I can tell just by turning the shaft. You can feel the wire. You can actually feel the wiper move along the wire. And that's the case with most wire-wound VRs. If you very carefully rotate the shaft, you can actually feel the wire. Listen to this one. It's pretty coarse. Definitely not suitable for RF either. This thing is a big inductor. This is a high-quality Allen Bradley control. This has got a carbon track, and the wiper has a carbon brush. So this would be suitable for RF if you wanted to use this in, say, a signal generator application or attenuator or something like that, depending on the resistance here. So this is just a general value that I picked up. So this would be suitable because it's a carbon track, and we're not really dealing with anything that's going to be turning into an inductor inside there. So knowing your VRs is very important. Again, you can tell a lot just by rotating the shaft very carefully. You can tell if it's wire wound or not, and also the application that it's in. If this, controlling quite a bit of current, a lot of the times they are a wire wound VR, and they vary in size, as you can see, quite a bit here. So I hope you've enjoyed this rundown on different resistors and how they work in different circuitry and under different frequencies and things like that. If you did enjoy this video, you can let me know by tapping the heart symbol below, and there'll be many more videos coming like this in the near future. We'll be talking about all sorts of different components and how they will operate and not operate in a lot of different types of circuitry. So until next time, take care. See you later.